Okay, so in this part, we're going to continue talking about the forms of concentration. So let's hit that next slide. Okay, so we just talked about molarity a lot, and now we're going to hit percent. So percent is a very useful metric, a very useful unit of concentration. And the thing about this one is it's specific. It's always grams for the solute and milliliters for the solution. I just realized, oh no, that this should say solution. I think I have that on all the next slides. Oops. Amount of solute over volume of solution, not just solvent. Okay, so in this case, it's always grams on the top and milliliters on the bottom. And then if it's percent, it's times 100. Right? So let's say you have 5 grams in 25 milliliter solution. And then so 5 over 25, right, is 0.2. So that makes it 20%. So if you have information, right, like you know the grams, you know the volume, you take grams divided by milliliters times 100. But if you're given the percentage, then that's equal to grams over 100. What I mean by that now, if given, is let's say you have, you're told you have a 5% dextrose solution. So 5% D5W. So D5W means dextrose 5% in water. All right, so it's 5% dextrose. What that means is that you have 5 grams of dextrose in 100 milliliters of solution. Okay. So you have to be careful where you put the 100. If you're trying to find the percentage, you take grams divided by milliliters times 100. If you're given the percentage, that is equal to grams per 100. Okay, and the percent means per 100, right? Now, when concentrations get smaller, in order to keep the number reasonable, right? Then we can introduce ppm and ppb, which are parts per million and parts per billion. In the same terminology, we could call this pph, right? Percentage is essentially just parts per 100. And so you take grams over milliliters times 100. ppm is grams over milliliters times a million. And so I think this came up in gases, right? That carbon dioxide is like 0.039%. But it's 390 ppm. So that's a number that, yeah, it's just generally just better than 0.039. That's pretty small. And ppb would be like the amount of lead in drinking water that's allowed is like 15 ppb, right? So it's really, really small, but 15 is a reasonable number to remember. But you use them just exactly the same way as pph, parts per 100, except you're just changing instead of 100, it's a million and a billion. Okay, so it's a little more to remember there, but it's still always grams per milliliter. Okay, now the third one. The third one is mass over volume. And this can just be anything. I mean, it's just entirely variable with metric prefixes, right? Notice all the metric differences here. And again, the whole point is just to make the numbers, the values that go in front of the unit, something reasonable, like between 1 and 10 or 1 and 100 or something like that. I think this list here are the actual ones that came off of uh, my report that I was looking at that I said had like 17 different units on it. These were all the different mass volume units of concentration. So, micrograms per milliliter, nanograms per milliliter, picograms per milliliter. That's really small. And then a deciliter. You might not remember exactly a deciliter, but it's 1/10 of a meter. So there are 10 deciliters in 1 liter, or you could say 1 deciliter is 10 to the negative 1 times liters. And so that's actually a pretty common one that we see. So there's the similar ones, micrograms, nanograms, milligrams per deciliter, milligrams per liter, grams per deciliter, all sorts of options. So this one has a lot of variability and flexibility. Molarity, pretty much one option, moles per liter. Percent, grams per milliliter. Also, ppm, ppb are common. And then mass volume concentrations are totally variable within metric prefixes. So that can make it a little bit harder, but it's fine. It actually allows more variability, and so that can be good actually. Okay, and again, now that you're at home, excuse me, you're at home. All this is in your textbook. There's a lot of examples that I'll point you to at the end of this, but um, basically, they have these three kind of sections just like this, and it's good practice to be aware of all of them. Um, in chemistry, molarity is almost always used. So if we're making a solution in lab or talking about a solution of acids, bases, and things like that, it's almost always molarity. But in healthcare, as you saw on like the report that I showed you and probably the reports that you've seen, mass volume and percent mass volume are much more common. And I want to give you one example that may help us to see why. So a patient's blood calcium level might be like, let's say 9.2 milligrams per deciliter. Okay, I actually wanted to walk through this. I forgot to remove the work. So what is the molarity? What would it be if we were chemists and we wanted to give molarity for the amount of calcium in blood? What would it be? So this is milligrams of calcium. Okay, so first let's what are the units of molarity? That's what we need to know. Right? Molarity, remember, is moles per liter. Okay, so we want to go from milligrams per deciliter to moles per liter. So you can do this as two separate things, right? We could take milligrams to moles and deciliters to liters and then bring them back together. Or we can keep it together like this and do one long string of conversions. So we're going to want to basically go, it doesn't matter which way you do it, but I'm gonna try to walk through doing it as one long string of conversions. Okay, so I'm gonna walk through the steps, And let's do the top first. Let's go from milligrams. We can convert that to grams. And then from grams, we need to get to moles, right? So we know that, well, we can do that somehow with molar mass, right? That would give us moles per deciliter. And then if we convert the bottom, we can get moles per liter, which is what we want. And so each arrow represents a conversion factor. So this one would be going from milligrams to grams. So there's our conversion factor. There are 1,000 milligrams in 1 gram. Then this would be going from grams to moles. So we need the molar mass of calcium, but we want to go from grams to moles. So 1 mole of calcium from the periodic table you can see is 40.08 grams of calcium. And this conversion factor would take us from deciliters to liters, which would be the fact that there are 10 deciliters per liter. Now notice I'm going from deciliters to liters, but I put deciliters on top. That's because this is already in the denominator, and I ultimately want liters on the bottom and deciliters to cancel out. Okay, so if we put this all together, sorry I ran out of room, but you should have it in your notes, right? We start with what's given, the known quantity, 9.2 milligrams per deciliter. And I'm going to just insert my string of conversion factors that I just wrote. Where now I have grams per deciliter. And then 1 mole of calcium is 40.08 grams of calcium. Gives me moles per deciliter. And then 10 deciliters per liter cancels out with this deciliters here. And what I'm left with is moles per liter. And we get 2.3 times 10 to the minus 3 molarity, or 0.0023 molarity, right? And that was 9.2 milligrams per deciliter. So the point here is that you can do these kinds of conversions back and forth all the time. And now you have the skill to do this because we've been doing this all semester. And 9.2 though is just a nicer number to say than 0.0023. It's easier to remember, and that's the point I'm making here. And I've made this point many times. So that's kind of the answer to our question, why. It's easier to understand, to remember, and to communicate these kinds of numbers. And remember, we just adjust and make up numbers or units to bring the values of these measurements into this range. So remember, atmospheric pressure was originally measured as the actual height of a column of mercury metal, and so 716 millimeters of mercury. And we're just going to call that 1 atmosphere. The average size of an atom is 1 times 10 to the minus 10 meters. Nah, we'll just call that 1 angstrom. The mass of a proton is 1.67 times 10 to the minus 27 kilograms. Yeah, let's just call that 1 AMU, and so on, right? So we do this all the time. All right, let's end here, and then we'll come back for a couple of example questions.